The night sky has always carried the illusion of permanence. Stars appear fixed, seasons repeat, planets return to familiar positions as if the cosmos itself respects routine. For centuries, astronomy has been the science of predicting that regularity of learning the clockwork so precisely that deviation becomes the only thing worth noticing. And yet, every so often, something crosses that clockwork without permission. Not a planet bound to the sun, not a comet shaped by billions of years of orbital loyalty, but a visitor moving too fast, arriving from the wrong direction, obeying gravity while seeming indifferent to belonging. In late December, NASA released a quiet update. New images, refined measurements, a designation still provisional, still cautious. 3I Atlas. If confirmed, it would be only the third known interstellar object ever detected passing through our solar system, a fragment not born here, not shaped by our star, not bound to return. The announcement carried no dramatic language, no warnings, no claims of danger, and yet, among scientists who track such things for a living, the response was restrained unease. Because interstellar objects are supposed to be boring. According to accepted models, the Milky Way should be littered with debris-frozen remnants ejected during planetary formation, wandering quietly between stars for billions of years. When one finally wanders close enough to be seen, it should look familiar. Cold, inert, predictable. A cosmic fossil, passing briefly through another system before vanishing again into interstellar darkness. That expectation was already strained once before. In 2017, the object now known as 1I Oumuamua crossed the inner solar system and refused to behave. It showed no visible tail, yet accelerated away from the sun in a way that could not be fully explained by gravity alone. Years of analysis followed, and while natural explanations remained plausible, the discomfort lingered not because the object was inexplicable, but because it was inconvenient. Science is comfortable with mystery when it arrives gradually. It is less comfortable when it arrives suddenly, moves quickly, and leaves before it can be fully understood. Now, years later, another object appears, not identical, not obviously related, but similar in the only way that matters: it does not fit cleanly into expectation. The new Atlas images show a faint point of light, grainy, modest, nothing cinematic, and yet hidden within those pixels is motion, a trajectory that does not close into an ellipse, but stretches into a hyperbola, signaling that this object is not gravitationally bound to the sun. It is passing through. Interstellar space is vast beyond intuitive comprehension. The average distance between stars is measured not in kilometers, but in light years. Objects traveling between them endure radiation, collisions with dust grains, and epochs of absolute cold. By the time such an object reaches another star system, it has been sculpted by processes far removed from planetary warmth or stellar familiarity, which makes its survival itself unremarkable, but its behavior anything but. Early calculations suggest a velocity higher than most solar system objects, a trajectory angled in a way that hints at an origin far from the plane of planetary orbits. These are not violations of physics, they are not alarms, they are simply facts that resist easy categorization. And science, at its most honest, does not dramatize facts. It sits with them. The images released on December 21 did not show propulsion. They did not reveal artificial structure. They did not imply intent. Any suggestion of that would be scientifically indefensible. What they did show was consistency, a consistency that sharpened questions rather than resolving them. As more data arrived, uncertainties narrowed, error bars shrank. Models converged, and still, the object refused to relax into familiarity. This is the subtle discomfort scientists are referring to when they speak carefully, when they choose words like unusual rather than impossible, unexpected rather than unexplainable. It is not fear, it is not excitement. It is the recognition that nature has once again presented a case study that sits just outside the boundaries of previous experience. Astronomy is filled with such moments. The discovery of exoplanets forced a rewrite of planetary formation theories. The accelerated expansion of the universe introduced dark energy, a placeholder name for a phenomenon still not understood. Neutrinos passing through Earth without interaction challenged assumptions about matter itself. None of these moments arrived with certainty. They arrived with tension. 3I Atlas, if confirmed as interstellar, does not threaten physics. It does not undermine gravity, relativity, or celestial mechanics. What it threatens is something quieter, the assumption that the rare will remain rare, and the anomalous will remain isolated. Because 2 anomalies can be dismissed, 3 begin to suggest a population. If interstellar objects are more common than previously believed, then our solar system is not a closed environment occasionally visited by cosmic debris. It is a crossroads, briefly intersected by fragments of other planetary systems, each one carrying information about distant stars we may never visit. And information in science is never neutral. It forces comparison, it forces revision, it forces humility. The Atlas survey was not built to hunt mysteries. It was designed to find threats near Earth asteroids, potential impacts, objects that could one day intersect our planet's orbit. In doing so, it scans the sky repeatedly, building a living map of motion against apparent stillness. It was never looking for an interstellar messenger. Yet here one may be. If this object proves to be natural and all evidence so far insists that it is, then it still represents something quietly profound, a physical sample of another star system, delivered without intention, asking no permission, offering no explanation. And unlike meteorites, which burn and fragment as they fall, this object will not be captured. It will not be studied in a laboratory. It will not wait. It will pass through the inner solar system, briefly illuminated by our star, and then it will leave carrying its answers with it. The unease scientists express is not about what this object might be, it is about how little time there is to know it. Every measurement must be taken from a distance, every conclusion must be provisional, every interpretation must survive peer review, skepticism, and the discipline of restraint. This is not a story about alarm, it is a story about patience. Because the universe does not reveal its secrets on demand, it offers hints, fleeting alignments, unexpected trajectories, moments when data resists simplification. And when those moments arrive, science does not shout. It listens. The discovery did not begin with mystery, it began with routine. On a clear night, automated telescopes scan the sky as they always do, comparing new images against catalogues built from countless previous observations. The system was designed to notice movement, faint points of light shifting subtly against a background of stars that appear fixed only because of their immense distance. This was the purpose of Atlas, the Asteroid Terrestrial Impact Last Alert System, a network of wide-field telescopes operated primarily to protect Earth, to provide early warning of objects that might one day intersect our planet's orbit. Its mandate was practical, almost mundane: find rocks, calculate risks, issue alerts. Atlas was not searching for interstellar visitors, it was searching for danger. When the object first appeared in the data stream, it did not announce itself as extraordinary. It was dim, barely distinguishable from noise, and moving at a speed consistent with countless minor bodies detected every year. The initial classification treated it as provisional, another candidate asteroid or comet awaiting confirmation. Astronomy advances not through singular images, but through repetition. The same region of sky is imaged night after night, and motion is confirmed only when consistent patterns emerge. False positives are common. Cosmic rays strike sensors. Reflections confuse algorithms. Most detections are discarded quietly. This one persisted. As additional observations accumulated, its motion became clearer. The object's apparent path across the sky could be plotted, and from that path, its orbit could be inferred. At first, the calculations assumed what astronomy almost always assumes, that the object was bound to the Sun. That assumption did not survive refinement. With each new data point, the orbital solution grew more precise and more troubling. Instead of closing into a familiar ellipse, the trajectory stretched outward, flattening into a curve that refused to loop back. When the eccentricity crossed a critical threshold, the implication became unavoidable. This object was not staying. An orbit with an eccentricity greater than 1 is hyperbolic. It signifies excess velocity, enough kinetic energy to escape the Sun's gravitational hold entirely. Such trajectories are rare within the solar system. When they occur, they usually result from gravitational interactions with planets, temporary slingshots that eject objects outward. But those objects begin their lives here. This one did not. Its inbound velocity was too high. Its direction did not align with the planetary plane. Its motion suggested an origin beyond the Sun's influence, beyond even the distant Oort cloud, that vast halo of icy debris thought to surround the solar system. The designation followed protocol, a temporary label, a numerical placeholder, a letter marking uncertainty rather than confidence. 3I, the third interstellar candidate. This alone did not provoke alarm. Interstellar objects had already been acknowledged as a reality. The discovery of One-Eye Oumuamua in 2017 shattered the assumption that such visitors would remain forever hypothetical. 2 years later, Borisov followed a more familiar comet, trailing gas and dust, behaving largely as expected. Together, they suggested that the Milky Way's debris field occasionally intersects our neighbourhood. What unsettled researchers was not that Atlas had found another one, it was how it appeared. The object was detected relatively late in its approach. Despite the sensitivity of modern surveys, it had slipped through earlier observation windows, either because of its faintness, its speed, or its trajectory through less monitored regions of sky. That delay compressed the timeline for study. Astronomy values patience. This object demanded urgency. Follow-up observations were requested from other observatories. Telescopes around the world were tasked with refining its position, brightness, and motion. Each new image reduced uncertainty, narrowing the range of possible interpretations. And yet, rather than converging toward familiarity, the data continued to hold its distance. Brightness measurements suggested a small object perhaps only a few hundred meters across, but size estimates depend heavily on reflectivity. A dark object appears smaller than it is. A reflective one appears larger. Without knowing its composition, astronomers could only bracket possibilities. Spectroscopy. The technique used to infer surface materials from reflected light was limited by the object's faintness. Signals were weak, noise dominated. No obvious chemical signatures emerged early on. This was not unusual, but it was inconvenient. What scientists hoped for, initially, was simplicity, a cometary spectrum, a dusty coma, something that would anchor the object within existing categories. Instead, early data offered ambiguity. NASA's December update did not announce conclusions. It offered refinements, improved astrometry, sharper constraints on the trajectory, confirmation that the hyperbolic path was real, not an artifact of sparse data. The tone was careful, the language restrained. Public-facing statements emphasized uncertainty, and rightly so. Interstellar classification requires precision. A small error in velocity estimation can turn an unbound orbit into a bound one. Claims are not made lightly. Behind the scenes, however, the conversation shifted. Not towards speculation, but toward comparison. How did this object resemble Oumuamua? How did it differ from Borisov? Why did it seem to occupy an uncomfortable middle ground, neither clearly cometary nor clearly inert? These questions did not imply exotic origins. They implied gaps in understanding. Astronomers are trained to distrust first impressions. They wait for convergence for independent datasets to tell the same story. With 3I Atlas, convergence arrived without comfort. The object's velocity relative to the Sun suggested an interstellar origin consistent with galactic motion. Its inbound direction aligned plausibly with stellar population models. Nothing about its path violated celestial mechanics. And yet, when placed into simulations of interstellar debris populations, it seemed uncommon. Not impossible, but statistically awkward. Interstellar objects are expected to be numerous, but small. They are expected to be ancient, but cold. They are expected to be dynamically simple. When something deviates from that template, it does not invalidate the template, but it does invite revision. The scientific response at this stage was not alarm. It was concentration. teams began modelling possible origins, ejection from young planetary systems, scattering during stellar encounters, fragmentation during close passes to other stars. Each scenario produced predictions about speed, spin, composition. Some predictions matched, others did not. Still, nothing crossed into the realm of impossibility. No laws were broken, no equations failed. What failed, quietly, was expectation. Atlas had done what it was built to do: notice motion where motion mattered. It had flagged an object that did not belong, not because it behaved dramatically, but because it behaved consistently in an unfamiliar way. The discovery phase, then, was not a moment of revelation. It was a gradual narrowing, the slow elimination of comforting assumptions. And as the data accumulated, one conclusion solidified. Whether mundane or extraordinary, this object would not allow itself to be ignored. It was already moving on. When NASA released the updated images, there was no spectacle to accompany them. No dramatic press conference, no urgent briefing, no language of warning. Just data. A sequence of faint, pixelated frames, a point of light barely distinguishable from the background noise of the cosmos. To the untrained eye, there was nothing there that demanded attention. To planetary scientists, however, the absence of reassurance was itself the message. These images were meant to clarify. Instead, they unsettled. Each new frame refined the object's position with greater precision. Astrometry tightened the error margins. The orbit became sharper, more confident. And with that confidence came a subtle problem. The object continued to behave exactly as the earlier, uncomfortable calculations had predicted. It did not slow. It did not curve inward. It did not resolve into a bound orbit once measurement uncertainty was removed. Hyperbolic motion remained. This alone would not have troubled scientists. Interstellar trajectories are rare but not unprecedented. What mattered was how clean the motion appeared. There were no obvious perturbations from unseen forces, no sudden changes attributable to observational error. The path was smooth, coherent, almost indifferent to scrutiny. And yet, there was something missing. Astronomers expect small bodies near the sun to reveal themselves. As sunlight warms their surfaces, volatile materials should sublimate, producing a faint coma or tail. Even minimal outgassing can often be detected through careful photometry. The new images showed none. At the distances observed, a comet of similar size should have displayed at least some activity. Even Borisov, detected further out, exhibited unmistakable cometary behavior early on. The absence here did not disprove a natural origin, but it narrowed the list of plausible compositions. One possibility was that the object was inert rocky, metallic, or depleted of volatiles after billions of years wandering between stars. Another was that its activity was too weak or too unusual to be detected by current instruments. Neither option was comfortable. Brightness fluctuations were subtle. There were hints of variability, but not enough to confidently infer rotation or shape. If the object was tumbling, it was doing so quietly. If it was elongated, the evidence remained ambiguous. The images did not contradict natural explanations. They simply failed to confirm them. NASA's update emphasized this restraint. The agency did not label the object anomalous. It did not speculate publicly. It acknowledged uncertainty, outlined next steps, and underscored the need for continued observation. But within the scientific community, conversation sharpened. Because these images arrived after lessons had already been learned. Oumuamua had taught astronomers the cost of hesitation. By the time its nature was recognized as unusual, it was already leaving the inner solar system. Opportunities for close study were missed. Hypotheses proliferated after the fact, constrained by limited data. This time, scientists were determined not to repeat that pattern. The unease surrounding 3I Atlas was not driven by fear of the unknown, but by awareness of how little time remained. The object was moving quickly. Its window of optimal observation was narrow. Every day mattered. Telescopes across the world adjusted schedules. Time was requested on facilities not easily obtained. Infrared observatories were tasked with detecting thermal emission, a potential clue to size and composition. Spectroscopic attempts continued despite low signal-to-noise ratios. And yet, as data accumulated, a pattern emerged that troubled researchers in a quiet, professional way. The object appeared boringly consistent. No jets appeared, no sudden brightening, no fragmentation. In astronomy, dramatic behavior often simplifies interpretation. A comet flares, and its nature is revealed. An asteroid spins rapidly, and its shape becomes apparent. Here, the absence of drama prolonged ambiguity. The object's non-gravitational acceleration, if present at all, was subtle enough to evade confident detection, unlike Oumuamua, whose trajectory displayed a measurable excess acceleration. 3i Atlas seemed to adhere more closely to gravitational expectations. But too closely. Models that accounted for radiation pressure alone could explain minor deviations, but only under assumptions about shape and mass that stretched plausibility. An extremely thin object would respond more strongly to sunlight. A highly reflective surface would alter size estimates. Each adjustment solved one problem while creating another. The images themselves offered no rescue. At this stage, alarm is too strong a word. Scientists are trained to avoid it. What they experienced was something more disciplined, a tightening of attention, a recognition that this object occupied a liminal space between categories. It was not defiant of physics, it was defiant of classification. And classification matters. Science advances by grouping phenomena, by recognizing patterns that allow one case to inform another. When an object resists grouping, it isolates itself, forcing explanation from first principles. The updated images, taken together, made one thing clear: this was not a fleeting artifact of poor data. The object was real, coherent, and behaving consistently with a specific, if unfamiliar, physical story. What that story was remained unclear. Some researchers quietly expressed relief. Unlike Oumuamua, this object did not immediately suggest unknown forces. Its motion could still be reconciled with accepted physics. There was no need to invoke radical explanations. Others felt the opposite. If the object was behaving normally, then why did it look so empty? Why did it refuse to reveal the telltale signs of composition? Why did improved resolution fail to add clarity? These questions were not rhetorical. They were technical, grounded in decades of small-body astronomy, and they led to an uncomfortable realization modern instruments, powerful as they are, still have limits. Atlas is a survey instrument. Its strength lies in coverage, not detail. Follow-up telescopes can resolve more, but only if the object cooperates, if it brightens, outgasses, or slows. This one did not. In internal discussions, scientists began to acknowledge something quietly unsettling this might be as much as they ever learn. Not because the mystery was unsolvable, but because the universe had offered only a glimpse. The December images were not alarming in what they showed. They were alarming in what they did not. They showed no violation of nature. They showed no comforting familiarity either. And that, in science, is often where the deepest questions begin. Because when data refuses to choose between interpretations, it forces humility. It reminds researchers that not every phenomenon will arrive with clarity, and not every visitor will linger long enough to be understood. 3i Atlas, in those faint frames, appeared indifferent to human curiosity. It neither revealed itself nor concealed itself deliberately. It simply passed through the field of view, obeying gravity, reflecting sunlight, and continuing onward. The alarm some scientists spoke of was not about threat. It was about misunderstanding. A recognition that the universe had once again presented something new, not loud enough to demand attention, but quiet enough to resist dismissal. And time, as always, was running out. Before this object ever appeared in a telescope's field of view, it already had a place in theory. For decades, astronomers had predicted that interstellar space should be filled with debris fragments left over from the chaotic process of planetary formation. When young stars ignite, they are surrounded by disks of gas and dust. Planets grow, migrate, collide, and scatter material outward. Much of that material never settles. Instead, it is flung away, escaping the gravitational hold of its parent star and joining the slow, silent traffic between stellar systems. These ejected fragments are expected to be numerous. Models suggest that every star may expel trillions of such objects over its lifetime. Collectively, they form a diffuse population drifting through the galaxy, invisible until one happens to pass close enough to a star to reflect detectable light. From this perspective, the existence of interstellar objects is not surprising. Their behavior, however, is expected to be. According to prevailing models, most interstellar debris should be small, irregular, and cold. Having spent millions or billions of years in deep space, their volatile compounds should be largely depleted or frozen beneath insulating layers. When they encounter a new star, any activity should be modest and predictable. Their trajectories should also reflect their origins. They should approach from random directions, but with velocities consistent with the average motion of stars in the local galactic neighborhood. Their paths should be smooth, governed by gravity, without sudden accelerations or anomalies. In other words, they should look boring. Comet Borisov fit this expectation almost perfectly. It arrived from interstellar space, displayed a classic cometary coma, released gas consistent with known compositions, and followed a trajectory that matched theoretical predictions. It was, in many ways, a vindication of decades of modelling, which made the earlier case of Oumuamua uncomfortable, but manageable. One anomaly can be absorbed. It can be explained as a rare outlier, a statistical fluke, or an extreme end of a distribution. The models could survive one exception. 3i Atlas now forced those models to look inward again. This object did not clearly contradict theory, but it strained the margins. Its apparent lack of outgassing challenged assumptions about volatile retention. Its brightness behavior complicated size estimates. Its detection window raised questions about how many similar objects might be passing unseen. The issue was not that the models were wrong, but that they might be incomplete. Interstellar debris is not a monolithic population. Objects can be ejected at different stages of planetary system evolution, under different conditions. Some may originate from inner rocky regions, others from icy outer zones. Some may be fragments of larger bodies shattered by collisions or tidal forces. In theory, this diversity should manifest in observation. In practice, astronomers had little data to confirm it. Until now. The problem with 3i Atlas was not its trajectory. That was well within expectations for an interstellar visitor. The problem was that its physical behavior did not align cleanly with any dominant category. If it was cometary, it was unusually inactive. If it was asteroidal, its interstellar origin demanded explanation. Asteroids, as understood in the solar system, form primarily in relatively warm regions where volatile ices are scarce. For such a body to be ejected from another system, it would need to survive close encounters with massive planets without fragmenting possible, but less common than icy ejections from outer regions. Comets, by contrast, are easier to eject and more abundant in the outskirts of planetary systems. They are the expected ambassadors of interstellar space. Yet this object did not behave like one. One proposed explanation was surface processing. Over immense timescales, cosmic rays and micrometeoroid impacts can alter an object's outer layers, creating a refractory crust that insulates interior ices. Such a crust could suppress outgassing until the object is extremely close to a star. This idea is plausible. It has precedent. But models suggest that even with such crusts, some activity should be detectable, especially with modern instruments. Another explanation invoked unusual composition. Exotic ices, such as hydrogen or nitrogen, could sublimate differently, producing less visible signatures. These ideas are not speculative inventions. They have been published, debated, and constrained by thermodynamic models. They also carry significant uncertainties. For example, solid hydrogen ice would sublimate rapidly, making long-term survival unlikely. Nitrogen ice has different constraints, and while it has been proposed for Oumuamua, it remains controversial. Applying such models to 3i Atlas requires assumptions that stack uncertainties atop uncertainties. Still, the fact that such explanations were being revisited at all indicated tension. The deeper issue was statistical. If 2 out of 3 interstellar objects detected exhibit unusual behavior, then either the detected sample is biased or the population itself is more diverse than expected. Detection bias is a powerful effect. Survey instruments are more likely to notice objects that behave oddly, that move faster, or that reflect light more efficiently. But bias alone cannot explain everything. Atlas and similar surveys are designed to detect motion, not physical properties. They do not preferentially select for inactivity or unusual acceleration. If anything, they are more likely to catch bright, active comets. The fact that this object slipped through earlier detection windows and then revealed ambiguous behavior suggested that something about interstellar debris might be systematically misunderstood. This did not imply new physics, it implied new statistics. Perhaps interstellar objects are not dominated by icy comets, but by processed, inert fragments. Perhaps the galactic environment alters surfaces more dramatically than models predict. Perhaps planetary systems eject more rocky material than previously believed. Each possibility fits within known physics. Each requires adjustment. And adjustment is where science becomes uncomfortable. Theoretical models are built on assumptions. Those assumptions are tested against data. When data accumulates slowly, revisions can be gradual. When data arrives suddenly in the form of rare visitors that refuse to behave, revisions become unavoidable. 3i Atlas did not overthrow expectations. It whispered that they might be incomplete. The object's behavior suggested that interstellar space is not merely a graveyard of frozen relics, but a place where objects evolve, age, and change in ways that terrestrial models struggle to capture. Radiation, time, and isolation do not simply preserve, they transform. This realization does not alarm scientists, it challenges them. It suggests that the solar system, long studied in isolation, may not be representative, that our local inventory of asteroids and comets reflects conditions specific to one star, one formation history, one galactic neighborhood. Interstellar objects are samples from elsewhere, and samples are only useful if their differences are acknowledged. As observations continued, expectations quietly shifted. The question was no longer whether 3i Atlas fit existing models, but whether those models were broad enough to accommodate what nature was offering. The object itself remained silent. It did not confirm, it did not deny. It simply continued on its path, a test case moving through theory, forcing it to stretch without breaking. If the images unsettled expectation, the mathematics deepened the unease. Orbit determination is one of astronomy's oldest crafts. From the earliest observations of planets to modern tracking of near-Earth asteroids, the process is deceptively simple in principle: measure position over time, fit the motion to gravitational laws, refine with each new data point. For most objects, the result converges quickly. The path becomes predictable. Uncertainty shrinks. With 3i Atlas, convergence arrived, but without relief. As more astrometric measurements were incorporated, the trajectory solidified into a hyperbolic curve unmistakably unbound to the Sun. This conclusion was not sensitive to small changes in assumed mass or reflectivity. It persisted across independent analyses and different computational methods. The object was not visiting temporarily, it was passing through. What drew closer scrutiny was not the overall shape of the orbit, but its fine structure. Subtle deviations from a purely gravitational path are expected for small bodies near the Sun. Solar radiation pressure can impart measurable force, particularly on low-mass or high-area objects. Outgassing can produce jets, nudging trajectories slightly over time. In many cases, these effects are unmistakable. The path curves just enough to betray their presence. Here, the evidence was ambiguous. Some solutions hinted at tiny non-gravitational accelerations. Others found none at all within the margins of error. The signal-to-noise ratio was low, and interpretations varied depending on assumptions about the object's physical properties. This uncertainty did not mean the data was poor, it meant the object was quiet. And quiet objects are harder to diagnose than loud ones. If the object was experiencing outgassing, it was doing so in a way that did not produce a visible coma or tail. If radiation pressure was affecting it, the effect was small enough to be masked by uncertainties in mass and shape. Scientists explored a range of models. A dense, compact body would be less affected by radiation pressure, A porous, low-density object would respond more strongly. Each model could fit the data, but only by adopting parameters that edge toward extremes. These were not violations, they were compromises. More troubling was the object's inbound velocity. When corrected for the sun's motion through the galaxy, it suggested an origin consistent with the local stellar population, but at the higher end of expected speeds. This did not make it impossible, but it made it less typical. Interstellar objects are expected to share the average motion of nearby stars. Deviations occur, but large ones are rarer. 3i Atlas seemed to occupy that rarer regime. Again, this was not a problem in isolation. It became a pattern in accumulation. Trajectory simulations traced the object backward in time, attempting to identify a plausible stellar origin. These exercises are inherently uncertain. Over millions of years, small errors amplify. Gravitational interactions with stars blur paths beyond reliable reconstruction. Still, broad trends can be assessed. In this case, no obvious parent star emerged. The object's path did not point cleanly back to a known stellar nursery or recent encounter. This was not surprising. Most interstellar objects will never be traced to a specific origin. But the lack of even a suggestive association reinforced the sense of anonymity. The object carried no obvious signature of where it came from. This anonymity extended to its motion through the inner solar system. It did not approach unusually close to any planet. It did not experience significant gravitational perturbations that might complicate interpretation. Its passage was clean, almost minimalist. For dynamicists, this was both a gift and a frustration. A gift, because the absence of planetary encounters simplified modelling. A frustration, because there were no external interactions to reveal internal properties. Sometimes an object's behaviour under stress tidal forces, close passes, heating reveals its nature. Here, stress was minimal. The object behaved like a test particle, which raised a subtle concern. If interstellar objects are common, and if many of them are small, inert, and quiet, then detection statistics may be misleading. Surveys may preferentially catch only those that are brighter, faster, or more reflective a skewed sample that misrepresents the population. 3i Atlas, by its very ambiguity, suggested that the visible fraction of interstellar debris might be just the tip of a vast unseen distribution. This realization did not alarm astronomers, it unsettled them. Because it implied that even with modern surveys, even with constant sky monitoring, humanity might still be largely blind to what passes through its own neighbourhood. The orbital behaviour of this object did not threaten gravitational theory. Newtonian mechanics and general relativity described its path perfectly well. There was no need for modification, no anomaly that demanded new laws. The discomfort lay elsewhere. Science relies on patterns. When enough data accumulates, patterns emerge, and exceptions fade into context. With interstellar objects, the data remains sparse. Each new case carries disproportionate weight. 3 objects do not define a population, but they can challenge assumptions about one. As researchers debated orbital solutions, they were careful with language. Terms like consistent with, within uncertainty, and cannot be ruled out dominated discussions. No one claimed the object was inexplicable. Yet no one claimed it was ordinary either. The orbit told a story of passage without engagement, a body entering from interstellar space, moving through the gravitational field of the sun as if on a schedule written elsewhere, and leaving without leaving much behind. In a sense, this was the most unsettling possibility of all. Not that the object was strange, but that it was typical, and that humanity's expectations had simply been too narrow. If this was what interstellar debris often looked like, then the solar system had been quietly intersecting with a broader galactic environment all along, unnoticed. 3i Atlas did not announce itself with fireworks. It did not demand explanation. It simply followed its path, forcing scientists to confront the limits of inference when behaviour is subtle and time is short. The mathematics was clear, the meaning was not. Inevitably, the comparisons began. Not because scientists wanted them to, but because memory is unavoidable. When a second unfamiliar object appears, it is measured against the first. When a third arrives, the comparison becomes structural rather than anecdotal. 3i Atlas did not resemble Oumuamua in any simple visual sense. There was no dramatic light curve suggesting extreme elongation, no clearly measured non-gravitational acceleration pushing it away from the sun, no sudden flare of attention that spilled into public speculation. And yet, the resemblance emerged where it mattered most in the space between explanation and certainty. Oumuamua had been discovered too late. By the time its interstellar nature was confirmed, it was already receding, its faint signal slipping beyond the reach of most instruments. What followed was a long afterlife of interpretation papers, models, debates, each constrained by data that could never be expanded. It became a lesson in scientific humility. At first, Oumuamua was assumed to be a comet, then an asteroid, then something in between. Its lack of a visible coma puzzled researchers. Its excess acceleration complicated matters further. Natural explanations proliferated hydrogen ice, nitrogen ice, fractal dust aggregates, radiation pressure acting on a thin object. None were definitively confirmed, none required new physics. But none were entirely satisfying either. The scientific community learned two things from that episode. First, interstellar objects could be stranger than anticipated. Second, hesitation costs understanding. With 3i Atlas, that lesson loomed large. Researchers were careful not to repeat mistakes, not to overinterpret, but also not to delay. Data was analysed in near real time. Models were run early. Hypotheses were constrained before speculation could outrun evidence. Still, the shadow of Oumuamua shaped perception. The similarities were subtle, but persistent. Both objects lacked obvious cometary activity at distances where it might reasonably be expected. Both resisted easy classification. Both arrived from interstellar space on trajectories that, while physically sound, felt statistically uncomfortable. And perhaps most importantly, both were fleeting. The danger of comparison lies in narrative inflation. Scientists are acutely aware of this. Two unusual cases do not define a trend. Correlation does not imply causation. Each object must stand on its own. Yet science does not operate in isolation. Patterns are how understanding grows. If Oumuamua had been alone, it could remain an outlier indefinitely. With 3i Atlas, it became part of a conversation not about aliens or exotic technologies, but about the nature of interstellar debris itself. Were these objects rare exceptions, or representatives of a poorly sampled population? Detection bias offered one explanation. Oumuamua was discovered by Pan-STARRS, a survey optimized to detect fast-moving objects near Earth. Borisov was discovered by an amateur astronomer scanning for comets. Atlas, too, prioritizes motion and proximity. These systems are not neutral observers. They favor certain trajectories, brightness profiles, and velocities. It is entirely plausible that the first interstellar objects detected would be those that are easiest to notice, not those that are most common. If so, then the similarities between Oumuamua and 3i Atlas might say more about human instrumentation than about the galaxy. But this explanation had limits. Borisov was active and cometary, exactly what models predicted. It was not quiet. It did not resist interpretation. If detection bias alone were responsible, then Borisov should not have been so different. Instead, the sample appeared heterogeneous. This diversity was not alarming, it was revealing. It suggested that interstellar space does not deliver a single archetype, but a spectrum shaped by formation history, ejection mechanism, age, and exposure to radiation. Some objects arrive as icy comets, others as processed, inert fragments. Some reveal themselves readily, others remain opaque. The problem was not that 3i Atlas resembled Oumuamua, it was that it resembled it enough. Enough to suggest that inactivity might not be rare. Enough to imply that surface processing could dominate observable behavior. Enough to hint that the galaxy's debris is older, harder, and more altered than once assumed. This realization forced a reframing. Rather than asking why these objects are strange, scientists began asking why expectations had been so narrow. Solar system comets are young by cosmic standards. They formed in a specific environment, under a specific star. within a relatively protected disk. Interstellar objects are not so fortunate. They are ancient, they are irradiated, they are battered by time. If Oumuamua and 3I Atlas share a resistance to activity, that resistance may not be anomalous. It may be the norm for objects that have spent eons in interstellar space. Still, caution prevailed. No claim was made that these two objects belonged to the same class. Their physical properties were not identical. Their observational signatures differed. Any attempt to merge them into a single narrative would have been premature. But neither could they be treated as entirely unrelated. Science advances by tension between comparison and restraint. Too much comparison leads to pattern-seeking beyond evidence. Too much restraint leads to paralysis. With 3I Atlas, the community walked that line carefully. The echoes of Oumuamua served as a reminder some mysteries cannot be resolved retroactively. They must be confronted while the data is still arriving, while hypotheses can still be tested, while the object is still close enough to matter. That urgency did not translate into speculation, it translated into discipline. The question shifted subtly but decisively. Not what is this object, but what kind of population could produce objects like this? That question was safer, more scientific, less sensational. It allowed researchers to expand models without abandoning rigor, to consider new distributions of size, composition, and surface evolution without invoking extraordinary causes. And yet, beneath the careful language, a quiet discomfort remained. Because if these objects are typical, if the galaxy regularly sends such quiet, ambiguous fragments through our solar system, then humanity has been missing most of them. Not because of negligence, but because of limitation. Oumuamua was not alarming because it was strange. It was alarming because it was fleeting. 3I Atlas carried the same lesson forward. Not as a warning, as a reminder. The universe does not repeat itself for clarity. It offers variations, hints, partial overlaps. Understanding emerges not from a single revelation, but from the accumulation of imperfect encounters. And sometimes, the most unsettling similarity is not behavior but the realization that even now, with all our instruments and equations, we are still learning how to notice what passes by. At first glance, the list of explanations seemed reassuringly familiar. There was no need to invent new forces or abandon established physics. Every behavior observed in 3I Atlas could, in principle, be explained using known processes. The challenge was not impossibility, it was sufficiency. Natural explanations were under pressure, not because they failed outright, but because each solved only part of the puzzle. The most straightforward possibility was that the object was simply inert, a rocky or metallic fragment, depleted of volatiles long ago, drifting through interstellar space until chance brought it close to the sun. Such objects are expected to exist. Planetary formation is violent. Collisions shatter worlds. Gravitational interactions eject debris. An interstellar asteroid would exhibit little to no outgassing. It would respond primarily to gravity. It would appear faint, quiet, and unremarkable. This explanation fit much of the data. What it struggled with was probability. Models of planetary system evolution suggest that icy bodies are more easily ejected than rocky ones. Outer regions are less gravitationally bound, and icy planetesimals are more abundant. While rocky ejections are possible, they are thought to be less common. Finding one is not impossible. Finding multiple may be suggestive. Another explanation focused on surface processing. Over billions of years, exposure to cosmic rays and interstellar radiation can alter an object's outer layers, chemically transforming volatile rich material into a refractory crust. This crust could seal in ices, suppressing sublimation even when the object approaches a star. Such processes are well studied. Laboratory experiments and solar system observations support them. Comets in our own system develop insulating layers over time. Interstellar objects would experience this effect far more intensely. This model explained the lack of visible activity without requiring unusual composition. It preserved the idea that the object might be icy beneath its surface, a dormant comet rather than a true asteroid. But again, the fit was imperfect. Thermal models suggested that at the observed distances, some level of activity should still be detectable, even through a crust. The absence of any measurable coma placed constraints on crust thickness and composition that were plausible, but narrow. The explanation worked barely. Radiation pressure was also considered. Sunlight carries momentum. For very low mass or high area objects, this momentum can produce measurable acceleration. In the case of Oumuamua, radiation pressure was one proposed mechanism to explain its non-gravitational motion. For 3I Atlas, radiation pressure effects appeared minimal. This suggested either a relatively dense object or one with a compact shape. Both were consistent with a rocky interpretation, but not definitive. Exotic ice hypotheses resurfaced cautiously. Hydrogen ice, nitrogen ice, or carbon monoxide ice could sublimate differently, producing less visible dust. These ideas were not speculative fantasies, they were grounded in thermodynamics and astrophysical environments observed elsewhere, such as on Pluto or in cold outer disks. However, they carried significant constraints. Hydrogen ice, for instance, would erode rapidly under interstellar conditions, making long-term survival unlikely. Nitrogen ice required specific formation environments and raised questions about abundance. Each hypothesis required tuning. None could be dismissed outright. None could be confirmed confidently. What scientists confronted was not a lack of explanations, but a surplus of fragile ones. Each natural model depended on assumptions about composition, structure, and history that could not be independently verified. Each could fit the data, but only if certain parameters aligned just right. This fragility did not imply error, it implied uncertainty. The scientific instinct in such situations is to search for additional constraints, more data, different wavelengths, longer observation baselines, anything that could eliminate some possibilities. But time worked against that instinct. As 3I Atlas continued its passage, its brightness faded. The geometry of observation worsened. The object moved into regions of sky less favourable for detailed study. Opportunities narrowed. The pressure on explanations increased. This was the point at which restraint mattered most. No reputable scientist suggested artificial origin. Such claims require extraordinary evidence that was entirely absent. The object obeyed physics. It did not maneuver, it did not emit signals, it did not exhibit structured behaviour. The discomfort came from a different place. Natural explanations were being stretched, not broken. This is an important distinction. Science does not require that explanations be aesthetically pleasing or perfectly balanced. Nature is not obligated to conform to expectation. An explanation that works under narrow conditions is still valid until contradicted. The issue was not that natural models failed, it was that they left little margin. This narrowness raised a deeper question: were scientists overfitting the data to preconceived categories? Perhaps interstellar objects simply occupy a broader range of properties than solar system bodies. Perhaps the dichotomy between comet and asteroid is an artifact of local history, not a universal classification. In that case, the discomfort surrounding 3I Atlas would not reflect a failure of explanation, but a failure of taxonomy. This possibility was quietly liberating. It allowed scientists to step back from individual hypotheses and reconsider assumptions. Instead of asking which known category the object fit into, they could ask whether the categories themselves were sufficient. The answer increasingly appeared to be no. Interstellar objects may not be neatly divisible into cometary and asteroidal classes. They may exist along a continuum shaped by age, radiation exposure, and formation environment. Some may arrive stripped of volatiles, others may carry them hidden beneath altered surfaces. In such a population, ambiguity would be common. 3I Atlas, then, would not be an exception. It would be a representative. This realization did not resolve the mystery, it reframed it. The unease scientists expressed was not about this object alone. It was about what it implied for future discoveries. If interstellar debris is often quiet, inert, and difficult to characterize, then even advanced surveys may struggle to extract meaningful information. The galaxy may be offering samples that resist easy reading. This is not a crisis, it is a challenge. Science thrives on such challenges, but only when it resists the temptation to overinterpret. The correct response to fragile explanations is not to abandon them, but to test them relentlessly and to accept that some questions may remain open. As 3i Atlas receded, the list of natural explanations remained intact. None had been eliminated. None had been elevated to certainty. That unresolved state was not failure. It was honesty. At this stage, the mystery no longer belonged solely to the object. It belonged to the instruments. Modern astronomy is often imagined as omniscient a global network of telescopes, satellites, and algorithms capable of seeing everything, everywhere, all at once. In reality, it is a careful negotiation with limitation. Every observation is shaped by sensitivity thresholds, cadence gaps, atmospheric distortion, and human choice. 3i Atlas exposed those limits with unusual clarity. Atlas itself is a survey system, not a microscope. Its wide-field design sacrifices resolution for coverage, allowing it to scan large swaths of sky repeatedly. This makes it exceptionally good at noticing motion, but less effective at revealing detail. When the object was first detected, it was already faint. By the time its interstellar nature was suspected, it was already moving away from optimal viewing geometry. Follow-up telescopes could refine position, but extracting physical information proved far more difficult. This was not a failure of technology, it was a reminder of trade-offs. Spectroscopy, the tool used to infer composition, depends on photons. Few photons mean weak signals. Weak signals mean ambiguity. Even the largest ground-based telescopes struggle when targets are small, distant, and fast-moving. Space-based observatories offer advantages: no atmosphere, stable conditions, but access is limited, schedules are tight, and sensitivity is finite. Not every interesting object can be prioritized. With 3i Atlas, astronomers pushed instruments to their limits. Infrared observations attempted to detect thermal emission, hoping to constrain size and albedo. Optical spectroscopy searched for absorption features that might hint at surface materials. The results were modest. Not empty, but insufficient. This insufficiency did not imply that the object was hiding something. It implied that human tools were operating at the edge of their design envelope. Interstellar objects, by their nature, arrive unannounced and leave quickly. They do not wait for ideal conditions. Astronomers are accustomed to long-term study. Planets return, comets recur, asteroids can be tracked for decades. Interstellar objects offer no such luxury. This asymmetry creates caution. When data is sparse and fleeting, scientists resist strong claims. They emphasize uncertainty not as a hedge, but as an ethical commitment. Overinterpretation is not just embarrassing, it erodes trust. In the case of 3i Atlas, restraint was especially important. The object occupied a cultural context shaped by earlier misinterpretations. Oumuamua had been thrust into public discourse prematurely. Its scientific ambiguity distorted into sensational narratives far removed from evidence. Researchers were determined not to repeat that trajectory. Thus, language became conservative. Papers emphasized limits rather than conclusions. Press statements highlighted what was not known. This caution was sometimes misread as alarm. In reality, it was discipline. The scientific method is not only about discovery, it is about boundary setting. Knowing where inference ends is as important as knowing where it begins. 3i Atlas forced astronomers to confront those boundaries explicitly. For example, shape determination often relies on light curves variations in brightness as an object rotates. For Oumuamua, dramatic fluctuations suggested an extreme aspect ratio. For 3i Atlas, brightness variations were subtle, noisy, and inconclusive. Was the object spherical, elongated, tumbling? The data could not say. Similarly, mass estimates depended on assumptions about density and reflectivity. Without clear constraints, size could vary by factors of several. A small, bright object and a larger, dark one could appear identical. Each unknown multiplied the next. This cascading uncertainty is not unique to this case. It is endemic to astronomy, especially at the frontier of detection. but rarely is it so visible. 3I Atlas became a mirror not of alien origin or cosmic threat, but of the limits of inference itself. Scientists responded by articulating those limits openly. They acknowledged biases. Survey cadence favours certain trajectories, detection thresholds favour certain brightness profiles, instrumental sensitivity favours certain compositions. None of this undermines the science, it defines it. In fact, such self-awareness is a strength. It allows future missions to be designed with clearer goals. It motivates new surveys optimised for interstellar detection. It informs the development of space-based platforms capable of rapid response. Already, proposals exist. The Vera C. Rubin Observatory, with its unprecedented survey depth and cadence, is expected to revolutionise small-body detection. It will likely identify interstellar objects earlier, giving astronomers more time to study them. Dedicated follow-up strategies are being discussed. Rapid response spectroscopy is being planned. 3I Atlas arrived just before these capabilities come online. In that sense, it is a transitional object discovered at the limits of current technology, pointing toward the need for more. The discomfort scientists expressed was not about what the object might be hiding, it was about what they might be missing. This is an important distinction. Science does not fear the unknown, it fears false certainty, it fears conclusions drawn too quickly, narratives built too confidently on incomplete data. In public discourse, ambiguity is often uncomfortable. It invites speculation. It creates space for misinterpretation. But within science, ambiguity is a signal not of failure, but of honesty. 3I Atlas lived in that ambiguous space. Not because it defied explanation, but because it revealed how much explanation depends on observation, and how observation depends on tools. As the object faded from view, the instruments returned to scanning the sky. Ready for the next motion that breaks the pattern. The data gathered would be archived, analysed, reanalyzed. Papers would be written, models refined. But no new photons would arrive. What remained was a record of limitation. And that record carried its own lesson, that even in an era of advanced astronomy, the universe retains the ability to surprise not by doing something extraordinary, but by doing something quietly, just beyond our reach. 3I Atlas did not challenge physics, it challenged confidence. And in doing so, it reminded scientists of a truth as old as astronomy itself, that knowledge advances not by eliminating uncertainty, but by learning to live responsibly within it. As observation slowed and uncertainty hardened into fact, the mystery entered a different phase. This was no longer about discovery, it was about consequences. By this point, the object's basic parameters were settled, its trajectory was interstellar, its motion was consistent with gravity, its physical nature remained unresolved. None of these conclusions were dramatic on their own. Taken together, however, they began to exert pressure on the framework scientists use to interpret small bodies. Not pressure enough to break them, enough to reveal their seams. The established taxonomy of solar system objects is a product of local history. Asteroids and comets are defined by composition, activity, and orbit. But those definitions emerge from a sample shaped by one star, one disk, one formation timeline. Interstellar objects, by contrast, arrive from systems with unknown architectures, unknown chemical gradients, and unknown dynamical histories. 3I Atlas sat at the intersection of those unknowns. It was not cometary enough to be a comet, not inert enough to be comfortably asteroidal. This ambiguity did not violate any law of physics. It threatened something subtler, the assumption that existing categories are universal. When models are built, they are built to explain what is known. They are then tested against what is discovered. When discovery drifts outside the model's comfortable range, the model does not collapse, it stretches. With interstellar objects, that stretching had begun. The question scientists now faced was not whether 3I Atlas could be explained, but whether explanations had been too narrowly framed. If interstellar debris occupies a broad continuum of properties, then forcing it into binary categories may be misleading. This realization carried implications beyond this single object. Population estimates of interstellar debris rely on assumptions about detectability. If many such objects are small, dark, inactive, and fast-moving, then surveys may be missing the majority of them. The few detected may represent a biased sample, not rare oddities, but the most visible tale of a vast distribution. If so, then the solar system may experience frequent interstellar passages without noticing them. This does not imply danger, it implies ignorance. The models of galactic debris flow may need revision. Not in their fundamentals, gravity still governs motion. Stellar dynamics still shape trajectories, but in their expectations of physical diversity. Interstellar space is not a static freezer. Objects moving through it are irradiated by cosmic rays, eroded by dust impacts, and chemically altered over immense timescales. Surfaces evolve, volatiles migrate, structures weaken or compact. The longer an object wanders, the less it resembles its origin. 3i Atlas may have been ancient, not just old in years, but old in experience. Its quietness may reflect not unusual composition, but extreme exposure. This idea does not break models, it complicates them. It suggests that interstellar objects are not snapshots of other planetary systems as they are now, but fossils of how they were long ago after billions of years of processing that erases clear signatures. That makes interpretation difficult. A fossil tells a story, but only partially. Much is lost. For scientists trained to extract meaning from patterns, this loss is unsettling. It introduces irreducible uncertainty. Some properties may never be recovered. Some origins may remain unknowable. This is not a failure of science, it is a boundary. The deeper discomfort surrounding 3i Atlas was the recognition that such boundaries may be common. As detection capabilities improve, more interstellar objects will be found. Some will be easier to understand, others will be as opaque as this one. Not every mystery deepens into revelation, some deepen into silence. This challenges a cultural expectation that science always converges on clarity given enough effort. In reality, convergence depends on cooperation from nature. When nature offers only fleeting glimpses, convergence may stall. This does not invalidate inquiry, it reframes it. The frameworks of celestial mechanics, planetary science, and astrophysics remain intact. Relativity is not threatened. Quantum theory is untouched. Cosmology is unchanged. What is threatened is comfort. Comfort with categories. Comfort with completeness. Comfort with the idea that every visitor can be understood. 3i Atlas forced scientists to confront the possibility that interstellar space may deliver objects whose histories are too long, too altered, too eroded to reconstruct, that some data gaps are permanent, not temporary. This realization is not dramatic, it is sobering. It invites humility not as a philosophical gesture, but as a methodological necessity. Models must account for what cannot be known, not just what can. As papers were drafted and discussions matured, language shifted again. The object was no longer described as puzzling, but as constraining. It constrained theories of interstellar debris. It constrained expectations of detectability. It constrained the ambition of interpretation. In doing so, it became scientifically valuable precisely because it refused to resolve neatly. This is an uncomfortable role for an object to play. Science often celebrates answers, but some of the most important advances come from recognizing where answers stop. 3i Atlas did not reveal new physics, it revealed the edge of existing understanding. And that edge, once exposed, cannot be unseen. Future detections will arrive in its shadow. They will be measured against its ambiguity. They will be interpreted with its lessons in mind. Some will fit comfortably. Others will reopen the same questions. The mystery, then, does not end with this object. It propagates. Not as alarm, not as speculation, but as a structural shift in how scientists think about interstellar matter. The galaxy is not offering clean samples, it is offering survivors. Survivors of formation, ejection, radiation, time. And survivors do not tell their stories easily. 3i Atlas passed through the solar system without incident. No disruption, no display, no legacy visible to the naked eye. Its impact was quieter. It altered expectation. And in science, Altered expectation is often the first step toward deeper understanding, even when that understanding must make room for what may never be fully known. Speculation entered the conversation carefully, almost reluctantly. By this stage, the boundaries of confirmed knowledge were clear. The object's trajectory was interstellar, its behavior was physically consistent, its composition remained uncertain. Any attempt to go further required stepping beyond direct observation into theory, hypothesis, and debate. Science allows this step, but only under strict conditions. Speculation must be grounded, it must be labelled, it must remain reversible. With 3i Atlas, researchers explored possibilities not because evidence demanded them, but because evidence failed to exclude them. One line of speculation focused on extreme surface evolution. Over interstellar timescales, objects are exposed to cosmic rays with energies far exceeding those common near stars. These particles penetrate material, breaking molecular bonds, driving chemical reactions, and altering mechanical structure. Over millions of years, such exposure could transform an initially volatile rich body into something chemically inert at the surface. In this scenario, 3i Atlas could be an icy body beneath a thick radiation-processed crust effectively sealed. Outgassing would be suppressed until deep heating occurred, possibly never reaching detectable levels during its brief solar passage. This idea is not speculative fiction. It builds directly on laboratory studies and solar system observations. What remains uncertain is scale how thick such crust can become, and how uniformly they form. Models vary. Some suggest crusts of centimetres, others allow for meters. The difference matters. A crust too thin fails to suppress activity. One too thick may be mechanically unstable. The data does not discriminate. Another speculative avenue involved unusual formation environments. Most planetary system models are derived from Sun-like stars, but the galaxy hosts a diversity of stellar types: red dwarfs, binary systems, dense clusters, each with distinct dynamical histories. Objects ejected from such systems may differ systematically from solar system debris. For example, material formed close to a low-mass star could be rocky, yet still easily ejected due to weaker gravity. Objects from dense stellar clusters may experience repeated gravitational interactions before escape, altering their structure. 3i Atlas may carry the imprint of such an environment not as a signature we can read directly, but as a deviation from expectation. This speculation is grounded in stellar dynamics, not imagination, but it remains untestable without additional data. More controversial ideas were also discussed quietly, cautiously, and explicitly as speculative. Exotic ice compositions, such as nitrogen-rich or carbon monoxide-dominated bodies, were considered. These materials have known sublimation properties that could suppress visible activity while still producing subtle forces. Such hypotheses gained attention after Oumuamua, but remain debated. They rely on assumptions about abundance and survival that are not well constrained. In scientific discourse, these ideas are treated as working hypotheses, not conclusions. They are valuable insofar as they generate testable predictions for future objects. Another speculative direction addressed structural porosity. Highly porous aggregates, sometimes called fractal bodies, could have low density and unusual thermal properties. Such structures might respond weakly to heating and show minimal activity. These models have precedent in dust aggregation studies and cometry science, but scaling them to hundreds of meters in size introduces uncertainty. Again, plausible, again, unconfirmed. What all these speculations shared was restraint. No hypothesis invoked new physics. No theory required abandoning established laws. Even the most exotic ideas remained firmly within the boundaries of thermodynamics, celestial mechanics, and astrophysical chemistry. Crucially, none were presented as fact. This distinction matters. In public imagination, speculation often blurs into assertion. In science, the opposite is true. Speculation is explicitly provisional. It exists to map the space of possibility, not to occupy it permanently. With 3i Atlas, that map grew wider, not deeper. Scientists did not converge on a favoured explanation. They catalogued options, constrained them where possible, and acknowledged where constraints failed. This approach frustrated some observers. It felt inconclusive. It lacked narrative closure. But it preserved integrity. The discomfort expressed by scientists was not that speculation was needed. It was that speculation could not be resolved. This is a subtle but important point. Speculation is comfortable when it points toward future confirmation. It becomes uncomfortable when confirmation may never arrive. 3I Atlas was already leaving. No spacecraft would intercept it. No sample would be returned. No experiment could be performed beyond remote sensing. The speculative landscape would remain hypothetical. And that was accepted. Science does not require every question to be answered. It requires that unanswered questions be identified honestly. The speculative theories surrounding 3I Atlas did not undermine confidence in natural explanations. They underscored the diversity of natural processes that may operate beyond the solar system, processes that our local experience has not prepared us to recognize easily. In this sense, speculation served a clarifying role. It showed that the mystery did not demand extraordinary explanations. It demanded broader imagination constrained by physics. As the object receded into darkness, speculation did not harden into belief. It remained suspended, waiting for future data from future visitors. This is how science moves forward when direct answers are unavailable, not by choosing a story, but by preserving multiple possibilities until evidence intervenes. 3I Atlas offered no final verdict. It offered a reminder that the universe is under no obligation to be legible on human timescales, and that speculation, when disciplined, is not a weakness, but a bridge between ignorance and understanding. By the time the phrase scientists are uneasy began to circulate, the data itself had already gone quiet. No new images were arriving with transformative clarity. No late-stage observation overturned earlier conclusions. The object was fading, receding into geometry and distance, becoming once again a point lost among many. What remained was not alarm, but a feeling harder to articulate. Unease is often misunderstood. It is not fear, it is not excitement. In science, unease arises when results are internally consistent yet externally uncomfortable when equations close, but intuition does not. 3I Atlas produced exactly that condition. Nothing about the object violated expectation in isolation. Every parameter fell within some plausible range. Gravity worked, radiation behaved, thermal models remained intact, and yet, taken together, the picture refused to settle. Scientists are trained to trust patterns. They're also trained to distrust them when samples are small. This tension sat at the heart of the unease. 3 interstellar objects do not define a rule, but they do challenge a coincidence. One active comet, 2 quiet passers-by, one easy explanation, 2 reluctant ones. The discomfort was not that nature seemed strange, but that it seemed selectively uncooperative. In private discussions and conference sessions, researchers returned repeatedly to the same quiet question: what if this is normal? Not normal in the sense of common, but normal in the sense of expected once enough examples are seen. If interstellar debris is often processed, inactive, and ambiguous, then the models built around fresh, solar system-borne objects may be insufficient. This possibility unsettled not because it threatened physics, but because it threatened familiarity. Astronomy has long relied on analogy. What we see here informs what we infer elsewhere. Planets around other stars were first imagined as scaled versions of our own. Comets were assumed to behave universally. Asteroids were thought to be simple. Each of these assumptions has already been revised once. Interstellar objects may demand another revision. The unease also stemmed from timing. This object arrived just before the next generation of instruments becomes operational. The Virasi, Rubin Observatory, space-based infrared surveys, and improved rapid response networks promise earlier detection and deeper characterization. 3I Atlas arrived too early to benefit from them and too late to be studied fully by existing ones. This temporal misalignment sharpened frustration. Scientists could see what might have been learned had circumstances differed slightly. A few months earlier the detection, a few magnitudes brighter, a slightly different trajectory. Small changes would have yielded large gains. Instead, they were left with a partial portrait. Unease also arose from public perception. After Oumuamua, the scientific community became acutely aware of how ambiguity can be misused. The absence of clear explanation invites speculation untethered from evidence. Researchers felt a responsibility not only to pursue understanding, but to protect it. This created an unusual emotional landscape. On one hand, curiosity pressed forward, on the other, caution pulled back. The result was a careful, almost restrained silence, a refusal to fill gaps with conjecture. That silence was sometimes misinterpreted as secrecy or alarm. In truth, it was professionalism. The discomfort scientists expressed was not about danger. Interstellar objects posed no threat beyond that of ordinary small bodies, and 3-eye Atlas passed at a safe distance. There was no risk, no urgency in that sense. The unease was epistemic. It came from recognizing a mismatch between the richness of theory and the poverty of data, between the elegance of models and the stubborn minimalism of observation. Science is most comfortable when discrepancies point clearly toward improvement. Here, the discrepancies pointed in many directions at once. This created a rare moment of pause. Not a pause in research analysis continued. Papers were written, models refined, but a pause in confidence. Confidence that the next object would clarify the last. Confidence that accumulation would quickly converge. 3-eye Atlas suggested convergence might be slower, and that realization carries weight. It implies that understanding interstellar debris may require not just better instruments, but patience, decades of observation, many visitors, statistical maturity. It also implies that some mysteries will persist not because they are profound, but because they are subtle. Subtlety is harder to resolve than spectacle. In the end, the unease surrounding 3-eye Atlas was not a signal of crisis. It was a signal of transition from expectation to adaptation. Scientists did not feel threatened by what they saw. They felt challenged by what they did not. And that challenge lingered long after the object itself had moved on. Even as 3-eye Atlas slipped beyond the reach of the most powerful telescopes, the scientific response did not slow. It widened. The mystery was no longer something to be solved by this object alone. It had become a test case, a reference point shaping how future encounters would be handled. Attention shifted from interpretation to preparation. What is science doing now in response? The answer is quieter than many expect. There are no emergency task forces, no classified missions, no dramatic reallocations of resources. Instead, there is coordination. Astronomers across institutions began to compare methodologies, asking not what they believed about 3-eye Atlas, but how they might do better next time. The object had exposed vulnerabilities in observational cadence, response time, and data integration. Addressing those vulnerabilities became the priority. One major focus is earlier detection. The sooner an interstellar object is identified, the more information can be extracted. Early detection allows observation at larger heliocentric distances, where volatile activity may begin. It enables longer light curves, better shape constraints, and more robust spectroscopy. To that end, survey strategies are being refined. Algorithms are being trained to flag hyperbolic candidates more aggressively. Cross-survey data sharing is improving, allowing motion anomalies to be recognized sooner. This is not theoretical planning, it is already underway. The Uneasy Rubin Observatory stands at the center of these efforts. With its deep, wide, and rapid sky coverage, it is expected to detect dozens, perhaps hundreds of interstellar objects over its operational lifetime. Its sensitivity will allow identification earlier in their approach, providing time that Atlas and Pan-STARRS could not. But detection alone is not enough. Another focus is rapid characterization. Once an object is flagged as potentially interstellar, follow-up must be immediate, optical, infrared, and radio observations need to be triggered within days, sometimes hours. This requires infrastructure, not just telescopes, but agreements, software, and coordination protocols. Such systems are being built quietly, incrementally. Space-based observatories are also part of the plan. Infrared platforms, less affected by reflected sunlight biases, can constrain size and albedo more reliably, Thermal measurements reduce ambiguity about composition. Future missions may include dedicated small-body interceptors, spacecraft designed to rendezvous quickly with newly discovered objects. These concepts remain speculative and face significant engineering challenges, but they are grounded in serious study. They are responses, not reactions. Laboratory work continues as well. Scientists are recreating interstellar conditions, radiation exposure, extreme cold, vacuum to better understand how materials evolve over time. These experiments inform surface processing models, helping to interpret ambiguous observations. In parallel, simulations are being refined. Galactic dynamics models are incorporating broader distributions of ejection velocities and formation environments. Instead of assuming sun-like systems as the norm, researchers are sampling a wider range of stellar types and histories. This work is not aimed at explaining 3I Atlas retroactively. It is aimed at falsification. What would disprove current hypotheses? What observations would rule out surface crust models? What signatures would eliminate exotic compositions? Science advances by identifying what would make it wrong. For interstellar objects, falsification requires statistics. One object can mislead, two can confuse, many can clarify. That is the long view scientists are now taking. There is also an acknowledgement that some questions may remain unresolved even with better tools. No matter how early an object is detected, its history may be too long to reconstruct. Radiation erases memory. Collisions erase structure. Time erases context. This acceptance does not discourage effort. It disciplines it. The goal is not certainty, it is constraint. To narrow possibilities, to reduce ignorance, to map the edges of what can be known. 3I Atlas, in this sense, has already succeeded. It has reshaped priorities without forcing conclusions. It has guided investment without dictating belief. It has demonstrated the value of restraint in the face of ambiguity. Science is often portrayed as a march toward answers. In reality, it is a negotiation with uncertainty, conducted under the rules of evidence. The response to 3I Atlas reflects that ethos. No alarms were sounded, no claims were rushed. Instead, the community adjusted its posture, leaning forward slightly, eyes open, instruments ready. The next interstellar visitor will arrive without warning. It may resemble this one, or it may not. It may clarify, or it may complicate. What matters is that science will be better prepared not because it expects something extraordinary, but because it has learned how easily the ordinary can evade understanding. The mystery continues, not in panic, but in preparation. In science, the most important question is rarely what is true. It is what would prove us wrong. As 3I Atlas faded from observation, attention turned toward that question with renewed seriousness. The mystery had not crystallized into a singular explanation, and that ambiguity demanded discipline. If future discoveries were to clarify rather than compound confusion, scientists needed to define clear standards for falsification. What evidence exactly would dissolve this mystery? The answer begins with behavior. If future interstellar objects are detected early and display unmistakable cometary activity, extended comae, dust tails, volatile signatures consistent with solar system comets, then the quiet nature of objects like Oumuamua and 3I Atlas would be reclassified as rare outliers. The discomfort would ease. The models would hold. Conversely, if inactivity becomes common, then models assuming volatile-rich interstellar debris would need revision. The mystery would not vanish, it would migrate. Another line of falsification lies in non-gravitational forces. If precise tracking of future objects reveals consistent, measurable accelerations that cannot be explained by radiation pressure or known outgassing processes, then something fundamental would be missing from current models. That would not imply artificiality, but it would signal incomplete understanding of small-body physics. So far, 3I Atlas has not crossed that threshold. Spectroscopy offers another path. Clear detection of specific surface compounds, silicates, organics. Ices would anchor interpretation. If future objects show spectra inconsistent with any known astrophysical material, then speculation would sharpen into necessity. Until then, ambiguity remains methodological, not existential. Shape determination is another test. Extreme geometries, if repeatedly confirmed, would challenge formation models. But confirmation requires clean light curves and long observation windows, conditions rarely afforded by fast interstellar visitors. This is why early detection matters. The most decisive falsification would come from statistics. If dozens of interstellar objects are observed and their properties cluster around familiar expectations, then early anomalies lose significance. If instead diversity dominates with many objects resisting classification, then the mystery deepens, but also clarifies its scope. Science does not demand immediate answers. It demands that questions be framed in a way that answers could arrive. 3i Atlas has already contributed to that framing. It has forced researchers to articulate what would count as success and what would count as failure. It has exposed where assumptions lie and how they might be tested. This is not uncertainty run amok, it is uncertainty under control. There is also a quieter form of falsification patience. Some hypotheses fade not because they are disproven, but because they become unnecessary. As data accumulates, certain explanations lose relevance, others gain strength. Over time, the landscape simplifies. 3i Atlas may eventually occupy a footnote not because it was unimportant, but because it was absorbed into a larger understanding. Or it may remain a marker, a reminder of when expectations first began to shift. Both outcomes are acceptable. Science is not a narrative arc, it is an adaptive system. What matters is that falsification remains central, that no explanation is protected from challenge, that speculation remains provisional. In this discipline there is comfort. Not the comfort of certainty, but the comfort of method. 3i Atlas did not demand belief, it demanded clarity about doubt. And in answering that demand, science strengthened itself not by resolving the mystery, but by defining how resolution would one day be recognized. When the object was finally placed within its widest context, the mystery softened not because it diminished, but because it became proportionate. 3i Atlas was not an anomaly floating in isolation. It was part of a galactic environment shaped by forces vastly larger and older than the solar system itself. To understand what it might represent, scientists stepped back beyond orbits, beyond models of small bodies, and looked outward. The Milky Way is not static. It is a moving, colliding, evolving system. Stars orbit the galactic center on paths influenced by spiral arms, dark matter, and gravitational encounters. Planetary systems form, migrate, and sometimes disintegrate. Over billions of years, this motion becomes a slow mixing process, scattering debris far from its place of origin. Interstellar objects are the physical evidence of that mixing. Every such object is the result of multiple epochs formation around a star, ejection during dynamical upheaval, and long-term exposure to interstellar space. By the time it enters another system, it has already lived several lives. This perspective reframes the mystery of 3i Atlas. Its quietness may not be unusual, its ambiguity may not be surprising. It may simply reflect the fact that the galaxy is old, far older than the solar system, and that its debris has been weathered accordingly. Galactic cosmic rays permeate space. They do not come from a single source, but from supernovae, stellar winds, and energetic events scattered across time and distance. Over millions of years, these particles penetrate exposed surfaces, altering chemistry, weakening structures, and erasing original features. Interstellar dust collisions, though individually insignificant, accumulate. Each impact chips away at surface layers. Each passage through dense regions adds damage. Over time, objects become smoother, darker, more inert. 3i Atlas may be less a sample of another planetary system than a sample of interstellar aging. This is a sobering thought. Astronomy often hopes that interstellar visitors will offer pristine insights into distant worlds, chemical fingerprints, formation clues, comparative data. But aging erases fingerprints. It blurs distinctions. It reduces complexity to survival. If most interstellar objects are survivors rather than messengers, then the information they carry is limited not by technology, but by history. This does not make them uninteresting, it makes them honest. They tell a different story, not of origin, but of endurance. The cosmic context also places human concern into scale. Interstellar objects have been passing through the solar system for billions of years, long before life emerged on Earth, long before humans watched the sky, long before telescopes existed to notice. Their passage is not new, our awareness is. 3i Atlas did not arrive at a special moment in cosmic history. It arrived at a moment in human capability when detection is possible, but understanding remains partial. This asymmetry creates tension. We are just advanced enough to notice what we cannot yet fully explain. In galactic terms, the solar system is not a destination. It is a crossing point, a star among hundreds of billions, each shedding debris into a shared environment. Objects like 3i Atlas are not visitors in a narrative sense. They are participants in a larger circulation. This realization deflates sensationalism. There is no intent, no targeting, no message. Only motion. When scientists speak carefully about such objects, it is not because they fear what they represent. It is because they respect the scale of what they are sampling. A single interstellar object does not represent the galaxy. It represents one trajectory through it. And yet, even one trajectory can reveal something essential. It reveals that planetary systems are not closed, that material moves freely between stars, that the galaxy is chemically and dynamically interconnected in ways once considered abstract. 3i Atlas in this context is not alarming. It is connective. It links distant stellar systems through shared debris. It reminds us that matter does not remain where it forms, that the boundaries between stars are porous. This cosmic perspective does not solve the mystery. It dissolves urgency. It allows scientists to accept ambiguity without anxiety, to recognize that not every object must be fully understood to be meaningful. Some are meaningful because they expose scale temporal and spatial conceptual. 3i Atlas did that quietly. It did not demand attention. It earned reflection. As it continued outward, back into interstellar darkness, it rejoined a population vast beyond counting. Countless fragments, each carrying traces of distant systems, each shaped by time. The mystery it leaves behind is not about what it was. It is about how small our sample still is, and how patient understanding must be when the galaxy itself is the archive. When the object finally slipped beyond meaningful observation, there was no moment to mark its departure. No final image, no decisive measurement, no closing chapter written in data. 3i Atlas did what interstellar objects have always done. It passed through, briefly intersecting human awareness, and then returned to the long, indifferent currents of the galaxy. What remained was not resolution. It was perspective. By the end, scientists were no longer asking what the object was in isolation. They were asking what it revealed about the relationship between knowledge and absence, about how science responds when nature offers only fragments. This is an uncomfortable space. Modern science is often celebrated for its power, the ability to detect gravitational waves, image black holes, map the cosmic microwave background. Against those achievements, an unresolved object a few hundred meters across may seem trivial. It is not. Because power does not eliminate limits, it exposes them. 3i Atlas forced a confrontation with one of those limits, the limit imposed by time. The universe does not slow down for observation. It does not wait for instruments to align or models to mature. It moves continuously, and sometimes offers only a fleeting glance. When that happens, science must decide how to respond. Not with invention, not with certainty, but with restraint. The unresolved nature of this object is not a failure of inquiry. It is a demonstration of intellectual integrity. Scientists resisted the temptation to overinterpret. They labelled speculation clearly. They acknowledged uncertainty without embarrassment. In doing so, they preserved something more important than an answer. They preserved trust. The mystery of 3i Atlas does not imply that reality is unknowable. It implies that knowledge is conditional, dependent on opportunity, cooperation, and scale. Some questions require not just better tools, but more time than a single encounter allows. And time, in this case, belonged to the object. Philosophically, this carries weight. Human curiosity often assumes that every phenomenon exists to be understood, that observation guarantees comprehension. The universe repeatedly reminds us otherwise. Some phenomena are transient, some are eroded by history, some carry their secrets too far and too fast. This is not cosmic cruelty, it is neutrality. The galaxy is not withholding information, it is simply vast. 3i Atlas did not arrive as a message or a warning. It arrived as evidence of motion of continuity between stars, of material exchange on scales that dwarf human experience. Its ambiguity reflects our position in that system. We are observers embedded in a flow we did not create and cannot control. Our instruments carve narrow windows into that flow. What passes through those windows is shaped as much by chance as by design. This realization does not diminish science, it grounds it. It reminds us that humility is not a philosophical add-on, but a methodological necessity, that knowing where knowledge ends is as important as extending it. In the years to come, more interstellar objects will be found. Some will be brighter, some will be closer, some will behave exactly as expected, others will not. Each will add a data point, few will offer closure. And that is acceptable. Because science is not a collection of solved mysteries. It is a living process, one that adapts to what the universe is willing to show, when it is willing to show it. 3i Atlas leaves behind no definitive story. It leaves behind a lesson. That understanding does not always arrive with clarity. That sometimes the most honest outcome is an open question, carefully framed and patiently held. And perhaps that is the deeper value of this encounter. Not the object itself, now lost to distance, but the reminder it offered while it was here that curiosity must coexist with restraint, that mystery can be approached without being conquered, and that the universe remains larger than any single explanation. The sky returns to stillness, the surveys continue scanning, the equations wait. Somewhere beyond the edge of detection, the object moves on unchanged by having been seen, carrying with it a history we may never fully recover. And in that quiet departure, science finds not frustration, but resolve. The sky does not remember what passes through it. Light fades, trajectories disperse, the vast mechanics of the galaxy continue without annotation or pause. Objects like 3i Atlas move on, not as characters in a story, but as consequences of physics momentum carried forward from events long erased by time. What lingers is not the object, but the encounter. For a brief interval, human attention intersected with something not made here, not shaped here, not destined to return. Instruments tracked it, equations described it, language tried, carefully, to hold it without distorting it. And then it was gone. This is how most cosmic encounters end not with answers, but with alignment, a moment when curiosity meets limitation and chooses honesty over completion. The universe does not rush to explain itself. It offers fragments, signals, passes by. It asks quietly whether we will listen without insisting on certainty. In the long arc of science, this moment will be small, one object among many, one case among future statistics, but small moments matter when they teach restraint. They remind us that mystery is not a failure state, it is a natural one. That not every question is meant to be closed, and not every silence is meant to be filled. Somewhere now, far beyond the reach of telescopes, the object continues its path indifferent to interpretation, unchanged by having been seen. It does not know it passed a planet that wonders. It does not carry meaning. It carries motion. And yet for those who watched, calculated, and waited, something shifted. Expectations widened, patience deepened, the boundary between knowing and not knowing became sharper and more respected. The night sky looks the same as it did before, but perception does not. Because once you recognize that the galaxy is not empty, that it is threaded with travellers, fragments, survivors, the stillness acquires depth. And in that depth, science continues its work, quietly, carefully, without hurry,